Hi, my name is Baishun, and today I'll be talking about recursion. Okay, so today I'll be talking about how Python determines the meaning of an identifier in a program, what happens to the runtime stack when the function is called, what happens when the function returns from a call, what are important parts of the recursive function, and what happens when a return statement is executed, and why we need to write recursive functions and what the computational complexities of various recursive functions are. So first, just to basically what recursion is basically um a function that calls upon itself. And a famous recursive function that most of you guys should know is the Fibonacci sequence, and this recursive sequence is basically just a n equals a n minus 1 plus a n minus 1 plus a n plus 1, a n minus 2, right? And then it starts with a1 equals 1, a2 equals 2, 1, and then a2 is equal to 1 plus 1, which is 2, a3 a4 equals 3, and so on. And in this function, it called itself multiple times. There are also functions that call upon themselves once. So to first show an example of a recursive function, we have like a simple sum. Um, so what this code will do is it will I'll show you the regular iterative way of getting the sum to a certain number or the recursive way. So if you just wanted to iterate regularly and get the sum, it would be um remember this is how you do a function. And this is just a simple recursive function, right? This I'm not recursive, iterative function. It takes in a number as an input, and then it runs a for loop, and then for each number up to that point, you would add that number. So that's the iterative way of doing it. But there's also the recursive way of writing this code. So how you would write it recursively is you would do, and then to show this how this works, you could also you ran this, you get 55, right? Because you put 10 in, so it'll sum from 1 to 10, and that'll be 55. Now let's move on to the recursive way. So how to do it recursively is how you write a recursive sequence. Is first you need to check for the base case because a recursive function will call upon itself until it reaches a base case where you just return a certain value so that the recursion stops and it doesn't go on infinitely. So the base case here is if n equals 0, because what we want to do is how to do it recursively is you're building upon the layers of itself. So how you would do this is you would do n plus my sum recursive n minus 1. And then when you call my sum recursive n minus 1, it would be n minus 1 plus n minus 2, and you would go all the way to 0 to get the recursive, to get the sum. So then the base case would be if n equals 0, because that's when you stop, right? You stop adding when n equals 0. So then all you need to do is if n equals 0, return 0. And that will stop the recursion from becoming an infinite loop. And then the rest of this is just return n plus my recursive n minus 1. And then what this does is it returns n. This is the number you have currently, and then all the numbers added up to n minus 1. So that's how you write a recursive sequence, right? This function is recursive because we called upon the same function within this function. Up here, it's not recursive because we didn't do that. We just ran through a loop. And you can also run this. You can also run this code to see that it works. There we have 55. So then that's how you would do a sum. So next, let's try to write the factorial. Just in case some of you guys don't know what a factorial is, a factorial is basically all the, like a sum would be all the numbers added up to that number. A factorial is all the numbers multiplied up to that number. So we have like n factorial, 4 factorial would be equal to 4 times 3 times 2 times 1. So can you guys first show me how to write this? Can you guys show me how to write this, a function of a factorial recursively, like this? Factorial. How would you guys write the function? You can put it in the comments. Okay, so to write this function, it would basically be the same thing as the sum, except for instead of plus, you just do times. So it would just be, yeah. In the base case, instead of it being 0, you want it to be 1, right? Because if we multiply something by 0, it'll just return anything multiplied by 0 will be 0. So instead of if n equals 0, it would be if n equals 1, return, then return n times minus 1, right? And it will just multiply till the next number before it. Like for example, 4, it would be, if we did factorial, if we called factorial 4, it would be 4 times factorial 3. 3 factorial 3 would be 3 times factorial 2. And then that would be 2 times factorial 1, which would return 1. And then it would go back to 4 times 3 times 2 times 1. So you can see, for example, if you wanted to 5 factorial is 120, and there we go, is 120. So the next recursive function we'll go over is the one that I just introduced earlier, which is the Fibonacci sequence. So basically, if you wanted to do a factorial, I mean not, if we want to find the Fibonacci sequence, it'd be like you wanting to find the nth number in a Fibonacci sequence. So and for the two, this time we have two base cases, right? Because remember, it started off with it starts off with the first two being 1 because in the Fibonacci sequence, unlike the two recursive functions that we went before, there's two values that you need instead of just one value. So we could either define the first two base cases as A1 or A2 or A0 and A1, and let's just go with A0 and A1. So if n equals 0 or n equals 1, turn 1, because that's what we want to return 1 because these are the two base cases where n is 1. And then else, or not, we don't need an else. We just return fib n minus 1, fib is 2. And then or actually this case, actually gonna set if n equals 0, return 0, and if n equals 1, return 1. And that'd be the same thing because then it would be 0, 1, 1, 2 instead of 1, 1, 2. And then you can run this show. So for example, if you want the 7th number of the Fibonacci sequence, you could do fib 7. And then we run this, be 13, right? Because fib 0 is 0, 1 is 1, 2 is 1, 3 is 3, 4 is 5, 5 is 8, and no, 6 is 8, and 7 is 13. Okay. Another recursive function we could do is finding the sum of digits of a number. So to do that, we can do this. Okay, can you guys tell me what the base case is? Or the strategy? Yeah. The strategy, right, to find the sum of digits of a number, um, it would be like you would find the rightmost digit and then divide by 10 and find the rightmost digit until all the way until there's no digits left, right? That's how you find the sum of no, digits of a number. So the base case is if the number is 0, because then if you add 0, it'll just be the same thing. Like no matter what. Adding 0 is like the identity property. So 0, return 0. That's the base case. Next, all we need to do is Is it returns, we get the sum of the rightmost digit because mod 10 is just the remainder when you divide by 10. So that would be the units digit. For example, like 46 mod 10 is 6. And then we would get the sum of the digits of n divided by 10 because this will be recursive by moving. It'll take out the rightmost digit. Like for example, 46 divided by 10 would be 4 in Python language, and that'd be the sum of the digits. And then it would be, again, it would return 4 because 4 mod 10 is 4, and then plus some digits 0, and then that would return 0. And then it would be 4 plus 6, which is 10. So we can run this, for example, by doing then we get 15, right? So how this would work is it would return 456 mod 10, 6 plus 45, some digits of 45, and then it would add 5 plus some digits of 4, and then it'd be 4 plus some digits of 0. Yeah, so that's how we want to write recursive code is first think of the base case, what will happen, where do we stop the recursion so that it doesn't go on infinitely, and then we need to think about how we call the function inside and keep going on in the base case. Like here we divide by 10 to move on to the next case. Here we just subtracted 1 and 2. Similarly, in Fibonacci and sum, we also subtracted 1. Another recursion you could do, pretty similar to the factorial, is if you want to find the power of a number, you could find the power of a number. So how do we do that? This time, unlike the other times though, we need two specific parameters for this function because we need to know what power we're at, so how many times we need to multiply it, and what the base that we're multiplying the number until, right? So we have num and we have power. The number is the base, and then p is what power you want to multiply it until, right? So like the other cases, it would be, for example, if you add 3, 4, we would have the base case be if p is 0, right? Because like 3 to the 0th power is 1. So then if p equals 0, we return 1. And then else we would just return num times power p minus 1. And this makes sense because we're multiplying it by the number because it's to the power, and then we are multiplying this by power times that number to the power of p minus 1, right? And that would just be equal to num to the power of p. And then, for example, to print this, we could do this. If 4 to the power of 7 is 16,384. That makes sense, right? 4 times 4 is 16, 64, 256, 1024, 4096, and 16,384. And we could also see like try 2 to the power of 8. That'd be like 256. So that's how you would write power of a number. And this is different because you need 2 parameters instead of just calling 1 parameter in this recursive function. So another type of um recursive function that you want to call that's is least common multiple of 2 numbers. So how would we want to write this? We want to write this by, we're gonna iterate it until we get a value. We'll keep dividing by a certain value until we get to a base case. So what do I mean by this? We have two, least common multiple has 2 parameters, right? Because we have 2 numbers that we're comparing. So we do LCM A, B. And then we can do T equals 5B, right? This is the remainder when A is divided by B. And then if T equals 0, A, because that means that, oh, I don't need the parentheses. A is divisible by B, right? Because, and we will just want to return A because that is the least common multiple because they're the same. But otherwise, want to return A times. And why does this make sense? Well, we want to find the least common multiple, and then T is the remainder when A is divided by B. So then we want to find the least common multiple of B and T and then multiply it by A because that will make sure that we find something that's a multiple of B. To show this, we can print. This makes more sense if we show like for 2 and 5. If we put 2 and 5 in this function, T would be 2 mod 5, which is 2, and T is not 0. So then now we return 2 times least common multiple of 5 and 2 divided by 2. And then to find the least common multiple of 5 and 2, we would do, calling the function LCM 5, 2, T would be 5 mod 2, which is 1. And T is not 0 again, so then we'll return least common multiple of 5 times least common multiple of 2 and 1 divided by 5. And remember, we multiplied all of this by 5 before. And then if you call that again, least common multiple of 2, 1, T would be 2 mod 1, which is 0. And then that'll just return 2. And then in the end, it'll just be 5 times 2, which is the least common multiple, 10. Okay. Does everything I've said so far make sense to everybody? Okay, yes. Similarly to least common multiple, we can also do a least common and greatest common divisor function. So again, we need two parameters. Does anybody have any ideas on how we would want to write this? How we would want to write this is greatest common divisor. It would be the you would want to divide out the numbers until they have like the same exact divisors, right? You want to divide by the extra divisors that we have. And how you do that is like this. So first we want to know which one is bigger, A or B, so that we can figure out the extra divisors. So how we do that is first we can call the min function and high. And then we have two base cases. If low equals 0, that means the greatest common divisor is just the high, right? Because 0 is divisible by every number. So another base case is if low equals 1. If low equals 1, that means that there's nothing in common because 1 is not divisible by any number besides itself. So we would have to return 1 because if A or B is 1, that means the greatest common divisor is just 1. Else, we want to return greatest common divisor of low, high. And why does this make sense? Well, firstly, if high is divisible by low, then high mod low would be 0, and then when we call it again, it would return the higher number, high, or in that case, it would be low, and then that would be the greatest common divisor. But otherwise, if high is not divisible by 0, then the mod is the extra when you divide it. Like, for example, if you had um, uh, like 6 and 9. High mod low would be 3, and because 9 isn't divisible by 6, and high mod low would be 3, and then that would be the extra stuff. And if what 6 and 3 have in common would be the greatest common divisor. So basically, it just recurses until we reach one of the base cases of low equals 0 or if low equals 1. So then, for example, if you wanted to print greatest common denominator of I would do it. We have 12. That's the greatest common divisor. And for example, if you were try to logic your way through this, print GCD of 2460, and then what it would do is low would be 24, high would be 60. Low is not 0 or 1, so then it would call GCD of low, which is 24, plus high mod low, which is 12. Right? 48 plus 12 is 64. And now when you run it, low would be 12, high would be 24, and none of them are 0. So again, it would run call GCD again, and it would be low 12 and high mod low, which is 0. And then when you call GCD for this last time, low would be 0, high would be 12, and then one of the base cases is reached, and 12 is returned. So that would be the greatest common divisor. Okay, another one we have is Pascal's triangle. Another example. And just for those who don't know Pascal's triangle is basically this thing. So we have 1, and then we go 1, 1. And basically what Pascal's triangle does is each value below is the sum of the two values above it. So firstly on the edge there's only one value, so it'd just be 1. But then for example here it would be the sum of 1 and 1, 2. Then 1, 1, 3, 3, 2 plus 1, 2 plus 1, 1, 1, 1 plus 3, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, right? And so on. Let's just do one more row to be 1. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. 5 plus 1 is 6. And it's 1. So then when we do this, we realize that we can't just use any simple values to do this code, because we need an array because each row has a different number of values. And for example, for the third row, we need the second row, so we'll need these two values. And for like the fifth row, we'll need the fourth value. So that's how we would. So basically, to recurse through this, we would again have an n, and then we would want to we would have an n, and then if n equals 1, we would return 1, right? The base case. But then otherwise, we would return the sum of the two values above, or however many values above that you have. This will make more sense when we do the code. Okay. We have Pascal, and remember, if n is 1, we have a base case, so you just return 1 because we're returning an array this time. But otherwise, and this is our array. And what we're going to do is we're going to keep calling on the array until n equals 0. So then do is we're gonna add to the original, we're gonna add to line. So how we're gonna do this is line dot end previous line I plus previous line. This makes sense, right? We're just appending the sum of the two values above, and that's why we need to iterate until length of previous line minus 1. Normally through iterations through entire loop you iterate until just length, but because we have an I and an I plus 1, we need to stop at value earlier. But this doesn't take care of the last value, right? Because the last value is 1, and this would only go up to, like, for example, if we had, again, like, we drew this. For the next value, this part only goes up to 1, 3, 3, right? Because it would sum these two, and we already had the 1 at the beginning. So we need to add a 1 at the end. So how we do that is just, we would do line dot append 1. And then we return line. That's how we would do this code. Then keep it here. Let's try the fifth row because we did that one, right? That was 1, 5, 10, 1, 5, 6, 10, 10, 6, 5, 1, I think, or yeah, something like that. Oh yeah, 1, 4, 6, 4, 1, and we can verify that ourselves again. One. And that would be, yeah. It's 1 behind because when we have 1, it would call this 1 instead of it being 0. Okay. Moving on, we have converting an integer to a string in any base. So we could this is like another method of doing recursion, right? Like when we convert from different bases to strings, we need to do it recursively because it's like it's similar to the sum of the digits of a number, right? We take the last part mod whatever base it is, and then we do the sum of that one divided by that number. So this function is very similar to the function that we had before of the sum of digits of a triangle. I'm not a triangle, of a number. We have two functions, I mean two variables, right? Because there's two things we need to know, two parameters. Um, the number we have and the base we're converting it to. So first we need to do that's just to allow the conversion to the string. That will allow Python to convert to the string automatically. So if n is less than base, right? That's our base case because that's the last value. Just want to return. And this is just like, for example, if n is 0, it would be the 0th index of the string. So it's just returning that part of the string. So that would be the bases. And then otherwise, so I'll clarify. This can only go work up until base 16. It won't work past base 17 because then you would need more letters. So then if n is less than base, that's the base case, right? Because that's just like the rightmost unit digit. So we just return that. And otherwise, you want to return and that's just returning the value that we have left over when we divide by base and then plus that's the value we have. That's the value we have left out. Like example of n mod base was 8, then we would want to return convert t string and the 8, and the 8th value would be 8 in the thing. Okay, so next we can try doing this by doing run this print. If that's inside it, we need to do it outside. We get B13, right? I mean not B13, B13. Because that makes sense. 2,835 is B would be 11. 11 times 256 plus 1 times 16 plus 3. So the important thing to note when writing these recursive functions is just to note the base case and how the next case relates to the current case. So for like some of these, we add the current case, like mod something, or we can append something about the previous case, or like divide or multiply or whatever it is. So yeah, just keep in mind in recursive functions, the base case and the recursive part. Okay, so like another example would be listing. And also find the sum of a list. And this is also pretty straightforward. How we would do this is from a list, we would just either add the first element or the last element and just delete that element off. And the base case is just when there's nothing left in the list. The length of the list is 0. And yeah. So how we would do this. We need this part specifically because the different parts in Python list like you could have strings and integers together, and we need to make sure that we're not adding like a string and an integer. So we need to make sure that it works. So first, what this is checking for is if there's a list within a list, right? Because then we need to sum up it together again. So this. We need to add all the recursive elements up and this the list of element into the total. But otherwise, then the outside. In this case, the base case is taken care of in the else, just element. And when the for loop is finished running, then that would return total. So the base case looks different here because the base case is like there is no list and it just runs through it smoothly and then it runs through the for loop. So there is a possibility that this actually doesn't run recursively if all the elements within data list are just all simple integers. Then it would just run through the elements within data list and add them. So for example, if we wanted to run this, do recursive list, we have different elements. 1, 2, we have like 3, 4, and some 5, 6. And it will iterate, it will call the iterating part again on this list. So when we run it, it's 21, right? 1 added up to 6 is 21. Okay. The last function that I'll talk about is harmonic sum. So what is a harmonic sum? A harmonic sum is the sum of the reciprocals of positive integers. So I'll show you an example in a second. This example. Reciprocal. So for example, the harmonic sum is what harmonic sum is. So this recursive function will be pretty simple. It'll be similar to, for example, just the regular sum function, but instead of adding n, it'll be 1 over n. So can you guys try to write this code? And we only have one parameter this time, right? Because there's only one thing we need to know, the number that we're adding. So So first, what's the base case? Base case is just if n equals 1, right? But in this case, we want to be a little careful because we want to catch other issues and not result in an error. So then that could be like if n equals 0. We only checked for if n equals 1, then it would return 1 divided by 0, which we know is not possible, which would return an error. So to avoid error, we would actually call if n is less than 2. And what this does is if there's any case like 1, 0, -1, it'll all be taken care of. So we'll just return 1 if that's the case, right? Because base case n equals 1, that'll just return 1. Then otherwise, we'll just also return 1. Otherwise, harmonic sum, we just return n plus -1. And why does this work? Well, we're just returning the value of that digit, the reciprocal, and adding the values of all the reciprocals up till 1 before that digit. Like, for example, the harmonic sum of 5, it would be 1/5 plus the harmonic sum of 4, and so on. So then to run this, do these results, right? So yeah, that will be all for recursive functions. So just to review, we went through a couple different types of recursion. So in Python, the recursion function is just when a function calls upon itself and it goes up until a base case. And whenever we're writing a recursive function, we always want to have a base case to check and return so that it doesn't run on infinitely, and then we want to call the function on itself again when we write this recursive function. And then we always want to make sure we know exactly what the parameters are and what we're doing. And we went through a couple different types, right? We have just a regular parameter of a number when it's a more simple case. For example, just want to do factorial or a sum up to a certain number, or like Fibonacci, you just call, but this one is interesting because you call it 2 times. And then we can also need 2 variables sometimes, so watch out for that, 2 parameters, because we have multiple things to keep track of. For example, power of a number, we need the base and the power it's going up to. And same with least common multiple and greatest common divisor, right? We need 2 specific values because it's 2 things that you need to get to a common divisor or at least common multiple. And then we also do that for converting an integer to a string. And then we can also have Pascal's triangle, which is a little bit different because we had to use a list. And then we also had like the sum of a list, and then lastly we did the harmonic sum. So hopefully today you guys learn more about how recursive functions work and how to write them. And these functions are useful because sometimes you can't know exactly how many times you need to call something, but you know when you need to stop. Like for example, the Fibonacci one especially is much easier and less complicated to write when you use a recursive function. And we know exactly when to stop. We know the base case. So always try to write recursive functions. They can simplify your code a lot when you don't exactly know when to stop. I mean, you know when to stop, you know the base case, but you don't know exactly like where the end is. Otherwise, if you were just to write it normally. So that will be it for today. I hope you guys learned something, and thank you.